changing gears a little bit. And as announced, I'm going to talk about some ideas how to use quantum processors to explore topological order. And the work that I'm presenting has been done in collaboration with Leo Liu, who is a PhD student in my group in Munich, Adam Smith, who was a postdoc with us in Munich and recently moved to Nottingham, and my colleague Michael Knapp, and then people from Microsoft and Google, so including Christina Knapp, Kevin Satzinger, and Pedram Rushan. So Kevin and Pedram were mostly conducting the experiments that I'm presenting. So let me get started and point out the difficulties of simulating quantum many-body problems. So in the simplest case, we might use methods like exact diagonalization, where we would have to build up the entire many-body Hilbert space, and the problems then arise from the fact that the many-body Hilbert space is growing exponentially with system size. And just to put this a little bit into perspective, if we have some Hamiltonian and we want to simulate either the dynamics of the Hamiltonian or finding the ground states, etc., then we are limited to rather small system sizes. So just to give some numbers, if we are considering a system, a spin 1/2 system, right? So for example, we want to simulate a spin model on the Kagome lattice, then on a pretty big computer, we are limited to take or give the order of 40 qubits. And in the recent years, there's lots of excitement because already currently available devices have the order of 50 or so qubits. And that's really great because, again, stressing the exponential growth of the complexity, just 40 qubits would require then 1,000 of these supercomputers, right? So that's a big step between those, and the promises are, of course, that the number of qubits is going up in the near future. So that brings up, I think, a lot of excitement about using these platforms for simulating those complicated quantum many-body problems that we are interested in. However, there are quite a few open questions still. So question about the scalabilities of these devices, and as compared to the computers that we are used to, at least the current days quantum computers are by far not as perfect, right? So if we write a program for a classical computer, we don't really worry too much about the length of the code, because we know that the computer is not going to forget part of the code while processing it, right? So the quantum computers, the classical computers are extremely reliable. And this is not yet given for the current generations of quantum computers. Still, I think it's quite exciting to think about what kind of problems can actually run well on so-called near-term noisy intermediate scale quantum devices, right? So basically one way to think, or one question that I find very exciting is now to wonder about what kind of problems might be the first ones where a quantum computer can actually achieve some useful results that we could not simulate on classical computers. And in this talk, I want to discuss some ideas that we played or that we entertained to use quantum computers for simulating sort of some key features of topological order. Before getting into the actual topic, I want to show some of our previous ideas about using quantum computers. And the reason that I'm showing this is also probably to lower a little bit the expectations, because what I'm showing now is my first real encounter with quantum computers, and that sets a little bit the bar. So when we got access to the first quantum computer to play with, the first idea that we wanted to try was to use the quantum computer to perform time evolution, right? So because we know that well, we heard of many examples throughout this talk where quantum quenches are quite useful to look at, right? So we just prepare some initial state and evolve it with some many-body Hamiltonian, and then we ask questions about thermalization, for example, and the like. So these are problems that are rather hard on classical computers, but surely if we use exact diagonalization, but also when using matrix product states, this is a very hard task, because in those cases, the entanglement is growing quickly, and one could talk a lot about it. But anyway, the idea is that let's do this exactly on a quantum computer. And these kind of problems have a very direct way of implementing them into the quantum computer, because if we have now some Hamiltonian, and for this Hamiltonian, we can now write down the time evolution operator for some short time step, and this we can just decompose using a Trotter decomposition into the application of simple two-side gates, right? So now we're assuming that this would be, for example, just the nearest neighbor Hamiltonian. And each of those gates can then be parametrized using elementary operations on the quantum computer. So we can have some C0 gates and some single qubit rotations. So we can just decompose those into fairly simple gates that are already implemented on the quantum computer, and then run the code. By running the code means that we just start from a simple initial state, and then we just evolve it in time. Good. So far, that's really straightforward. And let me just show some of the results that we got for conducting exactly this experiment. And the results that we are looking at now are after really optimizing quite a bit the kind of Trotter, the implementation of Trotter gates, and trying to use fairly large time steps such that we can get away with using only few qubits at only few, like a rather shallow depth of circuits. But these are the results that we are looking at. It's just an XY Hamiltonian. This is just the model of three fermions hopping in 1D. And we are preparing an initial state, which is a domain wall state where we have everything on the left pointing down, everything on the right pointing up. And we are now literally looking not at 50, but we're looking at 6 qubits. And here in this plot, we are looking at the evolution of spin number 6. And the initial state is in this domain wall state. So we start off with a polarized state here. And then if you just look at the exact evolution, this is a thick black line. And now we are comparing this to an exact evolution using the trotterization, right? So we just use the trotterization that we came up, we just use the trotterization, and now we just apply those gates exactly using a classical computer. And we find that, well, there is a fairly large Trotter error because of using fairly large time steps, but still we just can follow, at least qualitatively, the exact evolution of that spin. Now we take this circuit and run it on an IBM quantum computer. And then we just get the green line. And we see that fairly quickly after times that are not very long in terms of simulation, the signal is completely washed out, right? So we see that only really short times can be reached using this direct approach. So basically why I'm showing this is that it shows basically how careful we have to be when putting stuff or running stuff on current quantum computers, because the noise and loss of coherence and measurement errors, they are quite significant. So that tells us that we really have to work hard in order to keep the circuit depth really low in order to get good results. And in this specific case, we thought about doing this, and I just want to, without this going into detail, just flash the results. So basically motivated by the ansatz of matrix product states, abbreviated here as MPS, what we are doing is we are just writing down a very shallow ansatz where we have a sequential application of gates. And this, as we can show, is in a subclass of matrix product state with a bond dimension that's growing exponentially with the number of layers. So it's a class that is not easily representable on classical computers. However, time evolution can be efficiently compressed into these circuits with a very shallow depth. And then we see that the scaling is advantageous over a classical approach using matrix product states. Right? So while the number of parameters in an MPS would grow exponentially as function of time, this ansatz has a linearly growing number of parameters. And since this can then be done using very shallow circuits, we can then pre-process them, in this case, on a classical computer. And using these very shallow circuits, we can then run or simulate or just represent those states for rather long times on a quantum computer. So I'm showing these results just to make you aware of the importance of really thinking hard to keep the circuits really shallow, because this is what is doable with current quantum computers. But if we just directly translate whatever we have in our minds into something that we can run on a quantum computer, that is usually not working. So let me now come, having this in mind, to the main topic of my talk, namely the idea about exploring topological order on quantum processors. So now we have in mind that we want to do whatever we want to do using really shallow circuits. So we just want to think about how can we encode interesting information into really short programs that run on quantum processors. So as I pointed out, so I'm concerned now with studying topological phase of matter, and in fact, and throughout this talk, throughout this workshop, we've seen various of these examples. When we talk about topological order or topological phases, there are various things that we can have in mind. So there are symmetry protected topological phases, including topological insulators or spin chains, where we have topology protected by certain symmetries. We had fracton phases, as the one that we just heard about in the previous talk. And we have intrinsic topological order. And this is the class that I want to focus on now. And there are various representatives, like various examples that exhibit topological order, and these are most prominently quantum spin liquids or fractional quantum Hall states. So, and what I want to present is I want to use some noisy intermediate scale quantum devices to simulate these topological orders. There's a question in the chat about this blue material. This is a one-dimensional critical spin liquid. This is copper sulfate. It's a one-dimensional compound, and this compound is described in a good approximation by one-dimensional Heisenberg chains. And you can just crystallize, like make it yourself very, very easily by buying it in the pharmacy and grow these crystals. Okay. Let me now talk about the about a little bit, give me a little bit background about topological phases of matter. So topologically ordered phases of matter are characterized by their quasi-particle excitations. In particular, on top of the ground states of topologically ordered systems, we have quasi-particle excitations, so point-like excitations that obey fractionalized statistics. So these are anyons. So basically, if we just exchange them, they behave differently from regular bosons or fermions. And the bare presence of these excitations, these bulk excitations, has a number of important or characteristic properties. So the first one that I want to mention here is that the existence of such anionic excitations leads to the topological entanglement entropy. In particular, we have now a ground state of a gapped Hamiltonian, and to leading order, we are having an area law. So the entanglement entropy is proportional to some non-universal constant times the length of the cut. Right? So if we look at this example here, we can just, for example, do a bipartition of our system into two subsystems, subsystem B and subsystem A. And what we would get is to leading order that the entanglement entropy would be proportional to the circumference of this cut here. And in topologically ordered systems, we have some additive constant gamma. And this number of gamma is directly related to the anionic excitations that occur in this particular, in this kind of given topologically ordered state. And for the special case of having so-called abelian topological orders, where all the anyons obey sort of abelian statistics, or when exchange, all they do is picking up a phase, then this number gamma is directly related to the so-called total quantum dimension, or in this, well, this term is true in general, but in the case of abelian systems, it's just the logarithm of the square root of the number of anyons or different types of anyons that we have for a given type of topological order. This is then not a complete characterization of a given type of topological order, because there are different types of topological order that are sharing the same number of anyons. For example, a toric code model that we're going to discuss in a moment, and a double semion model, both have 4 different types of anyons. For both of them, the gamma would be log 2. So in order to distinguish a toric code topological order and a double semion topological order, we actually have to work harder, and we have to determine the exchange and also the mutual statistics of all different types of anionic excitations. Right, so we have now topological order, and topologically ordered phases are characterized by what kind of anionic excitations we have on top of the ground state, and the useful quantity to calculate is the topological entanglement entropy, but that doesn't fully characterize the phase. So on top of this, we would have to determine the exchange and mutual statistics of all those excitations. And for concreteness, let me now introduce a simple and very illustrative model that exhibits a topologically ordered ground state. And this is the toric code model. So the toric code model on a square lattice, as shown here, works in the following way. We take a square lattice, and we now have degrees of freedom. So we have some Ising spins that live on the bonds of the square lattice, as shown here. And the Hamiltonian now consists of 2 terms. So we have the vertex term A, which consists of a product of sigma z's bordering a vertex. Right? So it's just the product of sigma z on those 4 sigma z's for a given vertex. And we have a plaquette term acting on this plaquette, for example, where we have a product of all sigma x's. Now, this Hamiltonian has a very nice property that all terms mutually commute. Right? So this is obvious for all vertex terms because they're made out of sigma z's terms. So they clearly all commute. All plaquette terms also obviously commute because they're only made out of sigma x terms. However, it's not directly obvious that the A terms and B terms commute because they're having X and Z terms. However, if we look closer, the only problem that could occur is that if a vertex term and a plaquette term share spins, but whenever they're sharing spins, they're sharing a pair of spins, and then there are 2 intercommuting operators. So in total, it commutes. So we are fine. So we have now a system where all terms mutually commute. So it's exactly solvable. So we can just individually find the ground state of A and all A and all B terms. And the ground state of this Hamiltonian, now I have to be careful about the formulation. So if we actually have a system that lives on the infinite plane, has a unique ground state, and the unique ground state of this Hamiltonian is given by an equal-weighted superposition of all loop coverings. And when I talk about loop coverings, what I mean is that we just represent the spin configurations in the way that if a spin is pointing up, then we just leave this bond empty, and if this spin is pointing down, we just draw a red bar, and then the constraint that we get from the vertex term directly translates into having loop coverings. Good. So we have now a ground state, which is of the type that we have an equal-weighted superposition of all those configurations where there's an even number of spins up and spin down on each vertex. And on top of this ground state, we then have 4 different types of abelian anyons. And for this simple model, these kind of anyons are very easy to construct. So if, for example, we take the ground state and we act on the ground state with a string of sigma z operators of this type, then we find that this string everywhere commutes with the Hamiltonian, except at the ends where we are now creating an excitation. Right? So here, after acting on this operator with the ground state, we see that we are now creating an excitation of the plaquette term on this given plaquette. Or we can now also take a string of sigma x's that again commutes with all terms, except that this vertex here, then we just create another excitation, and that would be an excitation of this vertex. And now we just give kind of different names to these excitations. So if we don't have an excitation, that's the vacuum, which is just the one. If we have a plaquette excitation, we call it the M excitation. If we have a vertex excitation, it's an electric excitation. And if we have now a bound state of an E and an M particle, this is a so-called fermion excitation. Good. Okay, so this is now a simple, exactly solvable model where the ground state exhibits topological order. And what is the beautiful thing about it is we just know exactly how to create all the excitations. So the first task that we now have is that we set ourselves is that we want to find a code, or we want to derive a program for the quantum computer that generates the ground state of the toric code model. So this is now exactly following the spirit that we want to get something done with very shallow circuits. And here, because we have a prescription for the ground state, we don't have to use variational optimizations for the Hamiltonian, but instead we can just directly construct the ground state. And this is now done for on the chip. And let me just now walk you through the way how we can construct the toric code ground state on the chip. And I'm also gonna explain how what these kind of plots are representing. So what we see here in the background is actually the geometry of the chip that we are using. And this chip has the qubits where there are these gray zeros in the background. And this corresponds directly to the representation of the toric code before, when you just look at the black lattice. So now we see that we have qubits sitting on the bonds of our square lattice. And the initial state, and this is what comes directly when the quantum computer is turned on, then all qubits are initiated into a state where all spins are in the 0 state, or all qubits are in a 0 state, right? In terms of the Ising spins, that will maybe correspond to all spins pointing up. And now we can measure the parities for different plaquettes in this setup. And we measure now the Z parity on those plaquettes here that I'm now pointing at. And these are the plaquettes that live exactly around the sides of our square lattice, right? So these are exactly the vertex terms that we had before. And we see that simply the state where all spins are polarized, that is exactly the ground state of all vertex terms, because obviously every vertex has exactly 4 spins pointing up. So that's a perfect ground state for a plaquette, for the vertex. For the plaquette terms that are here, like the plaquettes that this is where we have the plaquette term defined. This is in this where we want to measure the X parity, like the product of all X's, and this is 0 for the polarized state. So this is clearly in an excited state. So this is not in the ground state. So now what we want to find is we want to find a simple procedure that builds the correct ground state of the toric code model using shallow circuits. And the simplest way that we could think of is the following. We first take the initiated state, polarized state, and we act with Hadamard gates on a subset of those spins here, like where the tops of those plaquettes. Following that, we then apply sequentially, starting from the center of this chain, the center of those of the slab, with C0 gates, and pulling it then from the inside to the like from the center to the left and to the right. And sequentially applying those gates, we are then left with a state which is exactly the ground state, which exactly corresponds to an equivariant superposition of all loop coverings. Right? So this, like for this kind of special for this case, we just know exactly how the program looks like that produces the ground state of the toric code. And the circuit that we have is then linear in the depth of the circuit is then linear in terms of the system width. So now we can apply this operator on the actual device and then measure the quality basically of what we got. And the quality is now extremely good because it's a pretty good quantum chip and the circuit is very shallow. So we see that after creating the ground state and then measuring all the stabilizers, measuring the vertex terms and plaquette terms, we see that the average fidelity is about 90%, right? So we have so basically what we see is that the ground state is prepared in a pretty decent way. So now that we have the ground state, we can then test the other thoughts. We can now characterize the state. And the first thing that we are doing is that we are going to look at the entanglement entropy. And in particular, we want to extract the topological entanglement entropy. And a convenient way to extract the topological entanglement entropy is to use one of these subtraction schemes proposed by Kitaev, Preskel, or by Levin and Wen. And the idea is that we just calculate these sort of mutual informations in such a way that all the local parts of the entanglement entropy cancel. Right? So if you just look carefully, this is chosen in such a way that all the local parts cancel, and the only part that's left is this topological contribution. So this we can now directly run on the device. So we just take the ground state that we produced on these 31 qubits, And we can now pick different partitions all over the place and measure the entanglement entropy. For small partitions, we can do this using full state tomography. So what's done in this case is that actually the reduced density matrix is sampled, and then we can directly extract from the entanglement entropies from the reduced density matrix. And this does not work for larger partitions, in particular not for this 9-qubit partition. And in this case, we use so-called randomized measurements to measure directly the second Rényi entropy. The upshot is, and this is plotted in this view graph, is that for all partitions, we actually find that the topological entanglement entropy is really close to the expected square root of 2. And this is now pretty independent of the size of the partition. And the scattering that we see here around log 2 depends on the spatial position where we just measuring it. So there is a certain variance over the chip as we just measure the topological entanglement entropy, but all measurements are pretty close to the expected value of log 2. And what I like about this is that this measurement shows that the ground state that we prepared using this procedure actually captures the right kind of non-local entanglement, this non-local entanglement that characterizes this topologically ordered state.
Frank, Claudio has a question. Claudio, do you want to ask a question?
Yeah, so in the plot of the fidelity, even though the average is high, but one can see that it decays from the center to the edges. Is it because of the edges? Well, the edge qubits are better, or is it just because the order of the gates, you start in the center and then you move on to the edges?
Right. I don't have a definite answer for you, but it is right that at the edges we apply fewer gates, so that certainly contributes to it.
Okay.
But it might also have to do with the quality. But indeed, I also believe, and this is what we think, it's because of the fact that we just apply fewer gates here.
Yeah.
Because I think that there are also fluctuations in the so the device has, like, for the device, certain qubits are better than others.
Okay. Yeah, I asked mainly because if it were the case that it decays as the earlier bits that you act on, they decay. That gives a bound on how big a lattice one can do given the quality of the qubits, right? Because by the time that you cover the whole system, some of the qubits are already dephasing.
Right.
But at least for this size system, it's very, very good.
Yes, I mean, and that's why I mean, this really struck me because this is also the talk why I was starting off with our first experiments that we did, where we just wanted to implement the time evolution, and we found on that device how quickly the fidelity decayed on that device, and here I was struck by how good it is, and even if you just look at the overall fidelity, global fidelity, it's the order of 0.3 or so. So it's incredibly good at this level.
Thanks.
Thank you. There's another question by Andrew about the largest partition that we looked at was 9. Is this a question or?
Yes, well, I want to know what the largest size was, but also whether, as you take a bigger patch over which you're doing a partition, whether the accuracy with which this topological entropy, entanglement entropy is extracted, whether that reduces. In the same way as sort of for the string order parameter in the 1D case, it decayed, the accuracy reduced. Do you see something like that, or?
Well, I mean, if you look at this plot, I mean, we actually see that it's not getting worse, right? So if you just look at the scattering, basically, if you look at the variance between different regimes where we do the measurements, it actually looks pretty decent still for the largest one. However, the sampling is also increased. So even if we just use this randomized measurements, the sampling that we have to do is increasing exponentially with the number of qubits. So it's getting more and more expensive. And the experimentalists, I think, were not happy when we were asking about using more than 9 qubits.
Okay, fair enough.
Mhm.
Thanks.
Thanks. And I mean, the toric code is, of course, special in this way that it has at least if we just get the exact ground state, the correlation length is 0, meaning that we should get exactly the same result for all partitions. It will, of course, be much more challenging when tuning away from this fixed point where we would have a finite correlation length, where we have to rely on larger bipartitions. Good. Let me next discuss the anionic statistics. So as I pointed out, in order to fully characterize the topological order, we have to not only calculate or measure the topological entanglement entropy, but also measure the anionic exchange statistics. And this is usually summarized in the U matrix, that is a diagonal matrix containing the phases that we get for exchanging two identical anyons, and the S matrix that contains the entries from moving one anyon of type A around some anyon of type B. So, and this, as I pointed out earlier when I introduced the toric code, we actually know exactly how to do for the for this simple toric code fixed point. So in this case, this is now an extreme shortcut. So what if we actually had some model where we wouldn't know exactly how to move these operators, we would rely on doing, for example, some adiabatic exchange that we just design a Hamiltonian where we have, for example, some point, like some potential that we would slowly drag to move around these particles. Here, however, we can just condense all this into applying a simple polystring to a state. And here is sort of a movie where we would do this in real time. So here we just have an anyon that we can really just move around another anyon by applying a string of Pauli axes. And here what you see are actual snapshots on the machine. So we started from a ground state where we now added an electric particle and a magnetic particle, and now a string is applied successively to move one particle around the other, and then snapshots are taken. Right? So what you see here, the color code is actually are measurements on the device. However, from these kind of snapshot measurements, we can't extract the phase that we get for the exchange. And in the order to do this, we are doing the following. We are adding now an extra qubit to our system. Right? So the chip that we are working on actually has about 50 qubits. So for creating the state, we only use 31. So we have some spare qubits that we can now use as ancilla qubits. So now we just prepare a state, which is a superposition of that ancilla state in the state 1 times the ground state plus this ancilla state in the state 0 times the ground state. Having prepared that state, we are then applying a controlled operation in such a way that if this extra state is in a state 1, we just move one particle around the other, while if this extra state is in a state 0, then we just don't do anything. And now from this measurement, or this kind of Ramsey interferometry as introduced in this paper, we can then read off or measure the phase that we get for this exchange process. So now we can do this for all the different cases discussed before, like for all different types of anyons. And this is now summarized in this plot. So here we just first look at the exchange statistics. So this is that we just exchange an E particle with another E particle, and they are sort of self-boson. So exchanging them, we just get a phase of 0. And the same for the magnetic particles. If we exchange them, we get a phase of 0. This is what we expect. If we take now a bound state of an E and an M particle together, they are a fermion. And indeed, we just pick up a phase of pi when we exchange them. And similarly, we can now look at the mutual statistics moving one anyon around a different type. And here, for example, we see that the moving one E particle around an M particle, we just pick up a phase of pi, right? So and the measured values are actually pretty close to the ones that we would expect. And let me stress, so what we are doing here is we are just shortcutting, because we do know exactly what the operators are that perform this exchange. However, in principle, we could also, if like the moment that we can reach deeper circuits, we could just play the same game where we actually would perform an adiabatic transport, right? So we would say that we would have a controlled operation of an adiabatic change in such a way that we just move one around the other particle. Okay, so basically this summarizes now the part where we characterize the topological order. And let me now just end by quickly flashing some results that we can now use this as what originally was proposed as a way towards sort of logical qubits. And the idea is that we use this toric code. This is like the original idea of using the toric code as a sort of fault-tolerant memory, where we just, instead of representing information in one physical qubit, we just now use the entire state to store the information about a single qubit. And for this, we are now choosing different boundary conditions such that we have a topological degeneracy, right? So we just choose the boundary such that we have now different topological sectors. And in this case, we can now look at the X parity along a string, or the Z parity along like this string here, like this loop around the torus. And we find that this actually nicely encodes the information of the qubit. So here are now states injected for different positions on the Bloch sphere and then read out. And we see that the phase comes out pretty well, while the amplitude is reduced due to measuring errors. And using this, we can now also perform some sort of passive error correction. And the idea is now the following: we can now encode some information on this toric code ground state by just putting it into a certain topological sector, and then read it out after a certain time. Right? So we just let it sit there, and then we just wait for a certain time, and then can read it out. And now we can perform some error correction. So let's say that we are doing a measurement here, and we see that in this case, there's some error, right? So we find that after a certain time that, for example, these two plaquettes are no longer in the proper ground state. So now what we can do is we can find the minimum number of physical qubits that we have to flip back to correct for these errors. And that corrects now the measurement output for this logical qubit information that we have stored non-locally in the ground state. And that this works can be seen in this slightly overcrowded plot. But let me just point to something interesting to look at. So, for example, if you look at these stars here, like the stars that you see here, this is now the raw measurement of the logical state 1 on a 5x5 grid. So this is the raw state without error correction. Now we just apply this passive error correction by just throwing away, or by fixing those states basically that where we had a problem, and then the error is just reduced by a factor of 5 roughly to the to these pentagrams, or not pentagrams, like these hexagon pentagons here. So we see that this passive error correction actually does significantly reduce the error rate and leads to somewhat more robust qubits. So let me now also point out, and this is some ongoing work, that the same ideas that we now demonstrated for the toric code can be directly generalized to general stringnet models. Right? So we can now also prepare ground states of general stringnet models, right? Double semion models or Fibonacci models. And for those, again, we can perform braiding operations in the same way as I just shown, like the kind of shortcut way of doing braiding operations, both for abelian and non-abelian anyons. Caveat, however, is that while the circuits still scale proportional to the width of those lattices, there's an overall constant which is much larger, and that prevents us from running it on current devices. But the hope is that this will be possible in not too far future. Good, and before closing, let me just end with an advertisement that I pointed out that there are various different types of topological phases. So now here I talked about topologically ordered phases, but I also mentioned symmetry protected topological phases. And here I want to advertise a talk by Adam given tomorrow, where he actually shows how to use shallow circuits to simulate symmetry protected phases and even kind of have then sweeps through quantum phase transitions. So let me close by thanking all my collaborators on this project, and let me close here by flashing the summary.
Okay, well, let's thank Frank for this great talk. I'm sure there'll be lots of questions. Let's see, any questions in the participants list? No, not just yet.
I have a question. It was in the chat, but I think it missed. So you showed this passive error correction. Is that just classical information you're correcting, or are you also correcting superpositions?
Well, here we just right. So here it's just basically classical, right? So we just measure the stabilizers, and that we know how to correct. So we can just correct Z errors or the X errors. So it's just based on those measurements of the stabilizers.
Okay, thanks.
It's written in the chat that the talk is if
Friday,
I said tomorrow, I mean
yeah.
Friday, as I
Friday.
Sorry.
Yeah, today's Wednesday. So let me ask a question. Where do you see this going next, Frank? Bigger systems, more exotic lattices?
Well, where I hope this to go is that, right, so what we are doing now is basically saying that at this point we have a pretty clear idea how to it's the wrong direction. So now we are in the position where we do have pretty good ideas how to generate the ground states, right? So here we take a model where we know exactly what the ground state is. So we have a model wave function. We have a toy state that we construct in the quantum computer, and we can show that based on this, we can extract information from the ground state. What I hope that things will going is that instead of taking model states, instead of taking toy states, that we can start from states where we, for example, choose a more general ansatz, that we just find efficient sort of trial wave functions that we can optimize with respect to some given Hamiltonian, such as we, for example, now optimize matrix product states or tensor product states, and that then starting from there, we can then characterize the topological order that a given system might have. So this is where I hope things will go. And for what's next, yeah, I mean, both IBM and Google, they promise to increase the circuit volume constantly. So the hope is that successively we will get closer to this result, but I don't know what the time scale would be.
Okay, very good. Other questions in the chat, or let me see what we have here. Everyone obviously found it extremely clear.
Could I just ask something I missed? When you prepare the toric code state, do you initialize all the projectors in +1, or do you let them be randomly +1 and -1 and then kind of classically reinterpret it? If you
No, here they are really all in the +1 state. So there are different ways to preparing the state using measurements, right? So this is not what we are doing here. So we are really, I mean, we are having a unitary circuit that creates exactly the toric code ground state in the end. So it's different from the measurement-based approaches, right? Because I think what you might refer to is we could start from this state, and then we just measure the plaquettes, and then we just write down the states, like the X parity states that we measured on the plaquettes. But this is not what we are doing here.
I see, thanks. And maybe just another quick clarification one. So did you say that when you do the interferometry, you're not actually moving an anyon? Or I missed how it worked.
Right, I think that I know what you want to ask. I mean, it's just that here, what I'm showing here for this movie, we just literally just sequentially apply those sigma x's, and we can just literally measure where the anyon is. However, then we just losing the phase information. So and what we are doing when measuring this phase, we're actually doing a control U operation, and U is actually the string that performs the entire exchange. So there's no intermediate step where we just could basically take a snapshot if this is what you're asking.
I see. I think I understand. Yeah. Thank you.
Gunnar, question.
I just throw in a question about the potential use of toric code models or other topological states as quantum memories. I mean, have you got an idea of what the fidelity rate is that individual hard qubits have to have in the hardware in order for this to become kind of a usable scheme in order to encode and retrieve quantum information?
But there are these general bounds, right? So I forgot the exact numbers, but that the fidelities have to be of the order of more than 90%. I forgot the exact numbers that are required for having proper logical qubits.
Mm-hmm. Okay, right. Anyway, so I was just wondering how close we are to actually, making this a viable opportunity.
I mean, I know that several groups are working on actually producing logical qubits. But let me stress, but in this example, it's more like a passive error correction. So it's here, I mean, this also may be a big important disclaimer. So if you just look closely at what I was showing, I'm not making a lot of references to the actual Hamiltonian, right? So here we are just making really use of the fact that we know what operators create anyons. We make use of the fact we know what the operators are that move anyons around and so on. And moreover, there's no energy gap in this system, right? So we don't have any Hamiltonian that protects these excitations from occurring. So it's really that we are just simulating what's happening in this model. However, the strength that I'm seeing, the fact that if for example, we would be able to do this adiabatic exchange, then we could just replace this control U operation by the adiabatic exchange, and it would still work. But there, the current machines would be, I mean, that I don't see how that could possibly work on using the machines that are available right now.
Right. But actually, I mean, the remark you make there about the energy gap, I mean, doesn't that generalize to any unitary circuit, right? Because, I mean, these are not energy-driven models, right? You can apply any operator at any stage.
That's right, yes.
So, I mean, even gapped states, right, will be somehow fragile to applying the wrong gates, right? I mean, mean, if you found the ground state of a gapped Hamiltonian and you apply some gate that is kind of mismatching, right? I mean, that will necessarily create excitations, but it doesn't as such cost any energy because there was no energy in the first place. Isn't that right?
No, that's really, I mean, this is also one thing that I find quite interesting is that that here we are really using the quantum computer to simulate properties of some Hamiltonian. It's similar when we are on a classical computer, we're using a Lanczos algorithm to find the ground state, and we are not using adiabatic cooling, right? So we're just using really tools that are different from what's happening in nature. We're just using the tools to understand certain properties of physical systems.
Okay, thanks.
Can you say a few more words about the underlying architecture of this computer? Is the qubits are superconducting qubits, and the switching is done using microwaves? Is that the way it's
This
working?
correct. These are transmon qubits,
Mhm.
and they're right. Switching is done using microwaves.
Okay.
Although I really have to say in this conversation, my knowledge of the details of the quantum computer are quite limited. It's just, I mean, I know that the level as I know how my Intel processor, my computer works. I just know the very superficial level. So all the tweaks on the machine and there were actually quite a few. I mean, this is also, I mean, what I found interesting when I write programs for the Intel processors in the cluster, I really don't have to worry about which bits I'm using because all bits work well. For the quantum computer, one really has to think about which bits, which qubits have the best fidelities, how to place the lattice onto the chip. So, for example, we wanted to use larger, or we would have been happy to use a larger lattice, but we couldn't because on the chip, this qubit that would be up here was not working. So we had to just shave off one line. I mean, there are all these kind of things which are different from running stuff on regular processors.
And you were able to do the programming all remotely and just submit it for running, or did you have to be on site?
For IBM, this is how it works. So for IBM, you can really just you write the program, and you can just run it first on a simulator, and then you change the flag, and then it's running actually on the quantum computer.
I see.
And usually you see that then the result is much more noisy than it was on the simulator. For Google, they do not have this yet. So in Google, this is a collaboration with a group from Google. And in this case, it was really that Kevin was doing the implementation. So we helped writing the program. So there's Circ, which is a programming language that has all these low-level functions built in, and Leo wrote the code, but then he sent it to Kevin, and Kevin was tweaking it to just make it work perfectly well on a given processor, and then he ran the results, and then he did the work on the machine. So we never submitted jobs ourselves for this.
I see. Very interesting. Okay, I see Andrew Green has his hand up. Andrew, do you have another question?
I do. Hi, Frank, again. It's a question I seem to ask you, I think, every time we chat, because I never quite understand the answer. But so the crucial thing for being able to get a quantum advantage in realizing states on these computers is that the states you're interested in form a shallow subset of the broader class of states. And certainly the string bond states, all string bond states are finitely contractible, and that's why you can get an advantage, and I believe you're going to have a paper soon where you show that generically. But do you think those string bond states saturate the finitely contractible subset of PEPs states?
The string bonds? Well, no, but wait. So you mean string bonds or string nets? Well,
I mean both actually. They have a similar, the reason they're finitely contractible is that there's an underlying 1D structure that you're contracting along, and these may form loops or lines or whatever. But if you take those two classes together, string bonds, string nets, do you think they saturate all the finitely contractible subset of PEPs?
Honestly, I don't know the answer to this because no, I don't know. But the thing is that there are, I mean, just sort of to make this clear. So these states that we prepare here, like these kind of toric code states, or also these general stringnet states, they are all very simple in the sense that they have a correlation length 0. And those are those kind of, as we basically can say that, like for these states, in principle, with a pen and paper, we can do this braiding.
Yep.
However, if we just take, for example, this prescription that we use here to create the states, now we can also add another layer of unitaries, like a sequential layer of unitaries that would add correlations to it. And then this would be a class of states that we would not necessarily be able to contract efficiently on classical computers. Right? So we can, and in fact, for those states, we also constructed an exact circuit that is shallow, and it actually goes through a phase transition between a toric code and a trivial phase. And again, on the quantum computer, it's easy to simulate. Well, pretty easy in terms of linear NL, but that would be hard to simulate than on classical computers.
You mean the equivalent state is slower to manipulate on the classical computer?
Right, that state would not be efficient because, I mean, this is kind of, if you have, for example, PEP states in 2D, then those might not be necessarily easy to contract. But I just give you a small PEPs, so I give you a something like this, and I say that these tensors now encode the information, like the solution to your problem. Then you still have to, in order to calculate expectation values exactly, it's still NP hard. So, and now in a similar way, I can just construct circuits that represent a state, and it still can be very hard for you to classically calculate what the properties are of the state. However, on the quantum computer, you can measure it.
Yep.
Okay. Any further questions? Well, in that case, let us thank Frank for 2 fantastic talks he's given us the last few days. And thank you very much. Cheers.
Thanks again for listening and for the discussion. Thanks.
Okay, let's see where we are.